Okay, so the question is about, is the channel static, and can an estimate of once be enough? And it all depends on the system you're using, what the situation is. Let's take wireless systems. In wireless systems, you would assume that the channel was changing in time. It's quite the norm. And you would run an adaptive filter, and you would update it periodically. Certainly, depending on what kind of system you're using in optics, there may be some effects that are changing. Maybe it's temperature effects. Maybe it's not. They're slow effects. Maybe there are other things that are changing in the channel. Maybe it's a reconfigurable network and things that could be changing drastically on the channel. It just depends. But the problem in optics is that the speeds are so high that running an adaptive filter is prohibitively expensive. And maybe with coherent detection systems this is less the case, and maybe we'll see this more, but it's still, there are already fixed effects that would have to be treated in DSP, and now getting time-varying ones would also be difficult. So maybe it's a compromise between what's actually going on in the system. And like I said, it just depends. It depends which channel you're talking about, and what you're willing to pay for in terms of processing. So in this paper in particular, it's an on-off keyed system, one that is going at the highest electrical bit rates that they could at the time, and doing any sort of adaptive version would be impractical in cost. And so they're looking for a very low-cost solution, which would be with a fixed filter. In this paper, here, the system that they simulated, and you can see it's very similar to the system that you'll be simulating in the homework. They're generating different pulse shapes. Here, they're doing, I think it's called a cosine squared, and this is what they call a practical NRZ. So, even the equipment cannot produce a perfect rectangular, that there's a pulse, that there are rise times involved in the equipment, and so this is sort of using a reasonable pulse shape. So they're doing pulse shaping before they transmit. Then they have an EDFA, where it introduces spontaneous emission, goes through an optical filter with a certain bandwidth, and they test different filter shapes. So they're looking at Fabry-Perot, and they're contrasting with Fabry-Perot grading filter shapes to see what impact that might have on your decision on what kind of low-pass filter you would use. And they use two kinds of low-pass filters. One is a RC circuit, a simple low-pass filter, and the other one is a Bessel. And they go and they put it through a threshold detector and count errors. So this was a good example of research where it would be very difficult to sweep through all kinds of filters in the lab. You would have to buy different filter widths, different precisions. It's something that's much more amenable to doing in simulation. So the issues that you're dealing with in the homework are similar to the issues that these researchers were dealing with in building a simulator for this system. That's all I had about this, just to motivate you to say that if you were interested, you could probably take our homework and actually just change the parameters if you wanted to create this. Also, that although this example is with on-off keying, filtering effects also has a large impact in coherent systems. Baud rates are being pushed, and they reach the limit of the frequency response of the components. It creates impairments. We try to get BSP to help. But certainly to achieve what we call Nyquist packing of the frequency, to get frequencies as dense as possible, one way is to use pulse shaping. So the Nyquist discussion is relevant, especially in the coherent detection systems that we're looking at today.